Hey everybody, today's talk is going to be on the chemistry of biology. Now, that may sound kind of weird, but if you think about biological organisms, they have to be made of something, and that turns out to be chemicals. And those chemicals, at their most basic level, are made of atoms, the simplest particle of all matter. So, just for example, in a human body, we're thought to have about 100 trillion cells that make up our body. But each one of those 100 trillion cells is thought to be made of about 100 trillion atoms each. So we can see that atoms, the basic building block of all matter, is extremely small. Okay? Cells on their own are very small, but atoms take it down even further so we can understand life and matter at a submicroscopic level. Let's get going. We're going to start off with the structure of an atom, and you can see a diagram here in the upper right. And what we can do is we can go over some review material for a lot of students, and we'll start with what we believe the yellow spheres to be within that diagram. And maybe the pluses are giving it away, but in middle school, most of us picked up there were these things called protons inside of an atom. There's also these orange ones that sit side by side with those yellow spheres, and these are called your neutrons. And lastly, we see a ring around the outside of those two particles in the middle containing some white spheres that seem to be connected to the ring. And those are going to represent our electrons of an atom. So ultimately, you have this positive core, and on the outside, you have this negative set of electrons. And that's how atoms are actually held together through the differences in those charges, the attraction of opposite charges of positive and negative. Now, in the center of this atom, we have what's known as the nucleus. So all those yellow and orange balls there together comprise our nucleus. All nuclei are made of protons and neutrons. So notice I changed the word to nuclei. That's plural of nucleus. And they tend to be very densely packed together. The area outside the nucleus, that's where you'll contain your actual electrons. Now, I got to break something to you here. The way we've depicted those electrons there, like they're on a ring, like planets around the sun, it doesn't work that way. But we draw it in that way because it's easier to understand for younger students, the fact that there is a number of electrons, they are on the outside, and there's a specific number of them. But in reality, the look of where those electrons exist is a little bit different. All right, now protons have charge associated with them, and that's positive charge. You can see that from the pluses on them. Electrons are negatively charged, and you can see the little tiny mini negative signs on each one of those white spheres. And then neutrons, they have no charge. They're actually neutral. So technically, a neutron is nothing more than a proton smushed together with an electron, and that's why they have no charge, because the positive and negative charge cancel each other out. Now, with this diagram, again, I got to be the breaker of some bad news here. It's not a great picture of how an atom actually exists. For example, I wrote something is way out of proportion. And that first something is this gigantic thing that we've been called a nucleus. Okay? Now, the nucleus in reality is very small. So if I was to put a tiny little dot right there in the center, you could hardly even see it. That, in relationship to the rest of this atom here, would be more typical of the size of a nucleus. So nuclei are very strong. So imagine I took a golf ball to the 50-yard line of a football field. Okay? That golf ball would basically resemble my nucleus. But my electrons that start outward from that nucleus would go all the way past the fan stands, past the parking lot, into the streets. That's how far the electron field from a single atom would go, from a golf ball sized nucleus on a 50-yard line. Okay, some people have even done some calculations and said, all right, if you had a beach ball on the surface of planet Earth, the electron field would stretch all the way up to the moon for a single atom. So that also brings in this abstract idea that atoms are mostly just empty space because these little electrons are so small. But we'll get into those ideas a little bit later. But for now, we've identified the nucleus is way out of proportion. There's also a particle that's incorrectly depicted, and we already mentioned those electrons don't float around in a ring. In fact, they have some really unique shapes of clouds they actually exist in, and I'll show you what that looks like right here. Okay, so right here you can see there's our nucleus. We're going to imagine it's a tiny little dot in the center to be more realistic about it. And then notice that you have some shaded rings here. Here's one ring, here's two, here's another one. Those are what we call electron clouds. And in electron clouds, you have a very good probability of finding electrons in there. But you also see these red lobes that almost look like flower petals sticking out. These are three-dimensional lobes, and these are also clouds where electrons would exist as well. So you can see this ring structure where they kind of go around and operate like a solar system doesn't work. But in fact, with today's knowledge that we do have, we know they exist like this due to calculations and other evidence that we found in the world of chemistry and physics. And they're not actually existing like we see here. But they're easier to understand, of course, when they're drawn like that. Here's one artist rendering of all the action going on within an atom. And if that was the case, our little dot right in the center there, that would be our nucleus, and all the rest of that space would be the electron field. And this is actually a real photograph from a very, very powerful electron microscope. The light blue color, that is actually those round rings of those spherical rings of electrons I was talking about. And then you got this little black nucleus here in the center. And the regions where you see the brightest colors are the regions where electrons actually exist. So this is the first photograph of a hydrogen atom. So we can actually see them now with our equipment that we've developed throughout the decades. This is a subatomic particle information table. Now, a couple of things. Number one, this word subatomic. Okay, sub means less than or below. Atomic means atoms. The only thing less than or below of an atom itself is going to be the particles that make it up. And that's where we have these three that we've already introduced in that first slide: the electron, the proton, and the neutron. Now, notice that each one of them has a much simpler symbol, E with a little superscripted minus, P with a superscripted plus, and then N with a superscripted, what looks like a zero to it. We couldn't call that naught, but just think of it as an N with a little zero above it. That's the easiest way for right now. The charges, electrons carry a 1 minus charge, so they're negative. Protons a 1 plus charge, and neutrons have no charge. They are neutral. Now, our masses, okay? So this is the weight of a single subatomic particle, like the weight of a single electron. Look at this number, 9.1 times 10 to the negative 28th grams. Now, first and foremost, the reason why the number looks like this is because it's in something called scientific notation. Scientific notation takes really, really large numbers and really, really small numbers and allows you to represent them easier on paper by hand or digitally, okay? So what this number really looks like would be a decimal point followed by zeros and zeros and zeros and zeros and zeros, and we'd have to have 27 zeros after that decimal point before we get to the 9 and the 1. So it would take a long time to write it, takes a long time to say it, so I'll just put a dot, dot, dot. Yeah, we don't want to do that. It's much easier to think of as 9.1 times 10 to the negative 28th power of grams. Now the proton, that's pretty small too, 1.6 times 10 to the negative 24th. Again, 23 zeros before you get to the 1 and the 6 after the decimal point. And then neutrons is basically the same. So in this last column, the mass relative to a proton, well, the proton's mass and the neutron's mass were basically equal, so we could say they have a 1-to-1 ratio. But look at the electron here. We have 1/1840th the size of that of the mass of that of the proton. So this is almost 2,000 times smaller, but here's the thing. Being 2,000 times smaller than a proton, it still carries an equal and opposite charge to that of the proton. So for a little tiny electron, it carries quite a punch. Equal and opposite charge to that of a 2,000 times larger proton. Just a little summary of that. So the neutron is large in comparison to an electron, has no charge. A proton is large in comparison with an electron with a positive charge, and the electron is very small in terms of a relationship with the proton. And in general, we know that all three of these are extremely small particles, but they do carry that negative charge. Next, we're going to talk about some fundamental ideas in chemistry, and these will hold through for us for biology because we use these terms all the times in biology as well. Chemistry is kind of thought of as the central science. It's like in the middle of a hub of other sciences all around it: earth science, physics, biology, you name it, and chemistry is usually right in the middle. So let's start with the definition of a substance that cannot be broken down. That's what we call an element in chemistry. And the smallest particle that can exist of an element, of course, is called the atom, the basic building block of all matter. And in part of its official definition, the smallest particle of an element that exhibits all the characteristic properties of that element. Now, we had said from the first couple of slides that atoms contain 3 subatomic particles. Get used to hearing that phrase, subatomic, smaller than atom. And those were the protons, the neutrons, and electrons. A little bit of repeat information here. Now, something we can add about the number of protons is that the number of protons equals what we call the atomic number of an element. Now, the atomic number is going to be found on periodic tables. And every periodic table has 118 boxes. Each box has a number at the top of the 118 of them, and that number corresponds to the atomic number. That's what we call it. And the atomic number equals the number of protons. So if I see carbon with a 6 above it on the periodic table, I know that carbon's atomic number is 6, and I know that it has 6 protons inside of it. Now, what we can also add here is that all atoms are neutral. Therefore, the number of protons equals the number of electrons. So again, if I was to utilize my carbon as an example, carbon has 6 protons, and it's going to have 6 electrons as well, okay? So if every atom is neutral, we can keep on doing that. Let's talk about neon. Neon is atomic number 10 on the periodic table. So neon has 10 protons, and it has 10 electrons, okay? All right, so all atoms are neutral. Let's move on. Here is a periodic table. Most of us have seen these before. There's some elements missing down here. This actually continues over this way here, and it goes up here. Sorry about the bad penmanship. My digital pen is a little quirky, but we'd keep adding numbers, and eventually we'd get to the number 118 up there. And the periodic table, like we said, is full of elements, and you can see the atomic numbers sitting above all those symbols there. So if I go over here to the right and 2 above this helium, that means that helium has 2 protons and it has 2 electrons because it's neutral. If I was to go ahead and circle this one here, selenium. Selenium has 34 protons and 34 electrons. Now, the periodic table is often broken into regions. I'll just give you those regions right now. In the middle, we have metals. So metals kind of take up most of the periodic table. They even work themselves over here a little bit. I'll put a little descending staircase there. So it's basically everything to the left, including this stuff here on the bottom. Some of the connections to living things, like we know as human beings, we don't have a ton of metals inside of us, but we do require some of these metals in very minute quantities called trace. Okay, trace minerals, trace elements to be healthy. So when we require something from this side, from this metal side, in small quantities, it's called a trace nutrient, trace element, trace mineral. Sometimes they're used interchangeably like that. But we do have some hard parts inside of us too that have metals, like calcium, for example. We know calcium's part of our body, you know where, in our skeleton, right? So in our bones utilize calcium quite a bit. And our body uses calcium as kind of a molecule, or an atom inside of us that opens gates on some cell doors and allows with the we'll call it electrochemical submission of messages, and we'll get into that a little bit later, but just know we do require some of these on this side. Then we have this kind of descending area right here called the metalloids, and they have properties between metals and that of what's known as nonmetals over here on the right, okay? So metals are shiny, they're dense, they conduct heat and electricity really well. Nonmetals, we got a lot of gases over here, some liquids, some brittle solids as well. And then metalloids kind of have properties in between. So a lot of different characteristics amongst all these elements here on the periodic table. While I'm here, I'll just kind of give you one little fact that plays into biology as well. I'm going to change this pen color here to a different color. And above this periodic table, I'm going to write this word right here, H-O-N-C, honk. Now, doesn't honk have a K? It does, but not when you're talking about the most prevalent elements in living things. In fact, H-O-N and C represent elements: hydrogen, oxygen, which is over here under nonmetals, nitrogen under nonmetals, and carbon under nonmetals. And these four make up 96% of all living things, including you. Okay? Now, some people even go a step further and they talk about this word called chomps. And chomps takes that percent even higher, probably 99%, because now you're adding phosphorus and sulfur to it, another couple of elements that are really prevalent in the human body. But honk, 96% of all living things are made of those four elements, and the extra 4% comes from the rest of the periodic table. All right, now each one of these boxes, you can see there's a whole bunch of detailed information there. The number on top, we already said it's the atomic number, which equaled the number of protons. But we also said all atoms are neutral, so the number of electrons applies as well. In the middle, we have a symbol. It can be a 1, 2, or 3-letter symbol based on a whole bunch of different things: where it was found, who found it, what language it was originally discovered in, and spoken, and then the name can be given as well underneath it. This one here doesn't have the names, but many periodic tables do. And then this number underneath it, this is called the atomic mass. We'll get into this one a little bit later, but ultimately we can say that a lot of the elements have different versions of themselves in different proportions around us on planet Earth. And you can factor all that in together and wind up with an atomic mass, which is kind of like a weighted average of all those different kinds of each element. Okay, more on that to come a little bit later. Okay, we are reaching the first of two I words today. This one's called isotope. And isotopes and mass numbers are kind of connected, and you're going to see why in just a minute. But let's talk about some subatomic particle matters again. All atoms of a given element have the same number of protons and electrons. Okay, we said atoms are neutral. However, the thing we didn't really talk about was the number of neutrons. So the number of neutrons may vary from that number of protons and electrons that we got from the atomic number. When that happens, you have what's called an isotope. Okay, now let's use carbon again for example. Carbon has 6 protons, it has 6 neutrons, 6 electrons, and carbon can have 6 neutrons, which would be nice, 6, 6, and 6. It can have 7 neutrons, 6, 7, and 6 then, or it can have 8 neutrons, 6, 8, and 6. And having those extra kinds of carbon reveals the isotopes of carbon. So what I want to do is I want to pay attention over here to this little diagram, and let's kind of talk through it for a second. We have a color code up here: red dots equal protons, blue dots equals green dots equals neutrons. And these are the isotopes of the first 3 elements on the periodic table. We have hydrogen, helium, and lithium. Now, we know these are all types of hydrogen because they all have 1 proton, and the atomic number guarantees the identity of a particular element. So by having 1 proton, your atomic number is 1. That guarantees you are hydrogen. This one also has 1 proton. That's hydrogen too, and so is this. Helium is atomic number 2, which means it has 2 protons. 2 red dots, 2 red dots. They're both helium. Lithium has atomic number 3, meaning 3 protons. 1, 2, 3, 1, 2, 3. Okay, so we know we've identified that this is hydrogen, helium, and lithium. Now, notice that in every single version of these 3 elements, you have a different number of neutrons. For example, in hydrogen 1, that's what this one's name is, there are no neutrons, so it's just 1 single proton, that's it. In hydrogen 2, you have 1 neutron, and in hydrogen 3, you have 2 neutrons. In helium 3, you have 1 neutron. In helium 4, you have 2. That's, again, the green dots. In lithium 6, you have 1, 2, 3. In lithium 7, you have 1, 2, 3, 4. Okay? So in each one of these elements, you have different number of neutrons, and that makes them isotopes of each other. Now, how does this matter for biology? Aren't we in life science? Yeah, we are. And not only do these isotopes exist all around us on planet Earth, but we utilize them all the time in our science and medicine as well. For example, When something dies and is long buried and we find that dead organism again, it will often have detectable isotopes in it. And if we go ahead and we do some calculations using some analytical machinery, we can figure out how long that organism's been dead based on isotopes that are still present in the cells that are left over. In the world of medicine, we can not only utilize isotopes to detect perhaps diseases or abnormalities, but we can also use it to treat some diseases and abnormalities. Sometimes hospitals will have a division in doctors' offices called nuclear medicine, where they have you either ingest some uniquely tasting isotopic material, or perhaps they'll inject it into a blood vessel, and then with some specialized equipment they look at your body on cameras and they see what's lighting up, and is it normal for that body part to light up, or is there extra activity in certain areas signifying there could potentially be something wrong. Some people who get cancer treatments, they have some special isotopes that give off energy, and they do so in efforts to kill those cancerous cells. That energy is not good for the cancerous cells, and it takes them out. So isotopes are useful in science all the time, and isotopes exist all around us at any given moment. All right, our next big term is called mass number. And mass number is the number of protons plus neutrons, okay? P plus N. And where we write it is actually sitting up here to the top left of every element symbol. So we superscript it up to the left, okay? And when that number, again, is the number of protons plus neutrons. And that should start to make sense as you look at the diagrams of the nuclei of these particular isotopes. Let's look at lithium-7 for a minute. It has a 7 up there. 7 is the number of protons plus neutrons. Protons are red dots, 1, 2, 3. Neutrons are our green dots, 4, 5, 6, 7. Protons plus neutrons. That's why there's a 7 there. Lithium-6, 1, 2, 3 protons plus 1, 2, 3 neutrons. That's why it's 6. And you can go through all these examples and see the same type of procedure being followed to write its mass number up there. Now, what do teachers ask when it comes time for seeing if you understand this? Well, they often ask how many neutrons something has, okay? Now, there is a simple formula for it. You can see it down here. Number of neutrons equals the mass number minus the atomic number. Okay, so let's think about that for a second. Mass number minus atomic number. And let's look at our examples. The mass number of this element is 7. Of this isotope is 7, right? Now, if I subtract its atomic number, remember protons, 1, 2, 3, 7 minus 3, of course, is 4. And let's double check and make sure we're right. 1, 2, 3, 4 green dots, right? So in lithium-7, there are 4 neutrons. Let's look at helium-3. Okay, we have a 3 up there. That's protons and neutrons. Let's take that 3 and subtract its atomic number. So 3 minus, in this case, 2 red dots. 3 minus 2 equals 1. Let's double check our work. There's 1 green dot there. Okay, so that makes sense. Okay, now let's say that you don't have a picture. Should we freak out if we don't have a picture? Nah, you shouldn't freak out. Let's imagine that you had 13 over the letter C. Okay, so 13 is the mass number, and carbon is represented by the element symbol C. So what I want to do is I want to subtract the mass number minus the atomic number. But what's the atomic number of C? What do I do? Well, remember we said that periodic table has all that information? You'd go look at the periodic table. You'd find out that carbon is atomic number 6. Put a 6 down here. And that's where you actually put atomic number. So we have 13 and 6. Watch this little trick. I'll put a little minus sign there. Little subtraction line. 13 minus 6 is 7. So carbon 13 has 7 neutrons. Without even giving me a green and red dot diagram, I figured that out. Okay? All right, let's try one more. Let's say there was a helium-5. Okay, let's say helium had an isotope with a 5 there. Let me make that HE a little bit better. Again, mass number is 5. Helium's atomic number is 2. I could look that up on the periodic table. 2. 5 minus 2, of course, is 3. So there would be 3 neutrons in that isotope. Okay, so now we're going to get to this place where we're going to name isotopes and write their symbols, okay? First of all, I've been using standard naming. Perhaps you noticed me saying hydrogen 1, hydrogen 2, lithium 6, lithium 7. That's called standard naming, and that's where you name the element followed by the mass number, and on paper you put a hyphen in between, a little dash, right? So we have carbon 14, chlorine 35, okay? Those are their names. Now, remember what we said, what teachers like to ask to see if you truly understand it. How many neutrons are present in each one of those? Well, for that, we're going to go ahead and we're going to have to put their symbol. Let's start with carbon. Here's carbon. I put a 14 up there. For my last slide, remember carbon was atomic number 6. So what I can do, put a little subtraction sign, subtract down 8 neutrons. Okay? Chlorine 35. All right, so we got 35. We have chlorine symbol, it's Cl. And we know its atomic number by looking on the periodic table, and it's 17. Okay, so if it has 17 protons and 35 is its mass number, we subtract down. 35 minus 17 is 18. So chlorine 35 is 18 neutrons, okay? This is what we call standard naming. Element's name followed by a dash or a hyphen followed by the mass number. Next, and I actually like these better, the nuclear symbols. Nuclear symbols give everything away because they have the mass number over the atomic number followed by the element symbol, okay? So when you write those, you have all the information you need right here. Look at, here's your mass number, here's your atomic number placement. Subscripted down to the left, you have your element symbol. And if someone was asking you how many neutrons are in this one, it's already set up for you. Literally, all you have to do is put a little minus sign there, put a little line there. Oh, 4 minus 2, that's 2. It has 2 neutrons, okay? But this is overall, big picture, this is called the nuclear symbol way of representing particular isotope. And then the last thing here, we've mentioned this a whole bunch of times. Occasionally you'll get only a element symbol with just a mass number. Why should you not freak out? Once again, imagine you had, let's say you had 21 Ne, okay, and that you didn't have the atomic number there. Remember, you have a periodic table. You can just look at the periodic table, look up Ne, and say, oh, it's atomic number 10. So you put its atomic number right underneath it. There you go, 21 minus 10, 11 neutrons. Okay, nice and easy. Our next topic revolves around the fact that most of the periodic table is not happy. Okay, that sounds kind of weird, right? So we got 118 elements and most of them are not happy. Yes, okay. They're kind of anxious. They kind of got a lot of nervous energy. So what they do to get more comfortable is they form bonds with other atoms, okay? Chemical bonds are forces that hold atoms together, and they do this to become more stable. They do it for stability. All right, so bonds that result from attractions between oppositely charged ions are called ionic bonds. They exist in ionic compounds. Wow, there's a lot of new stuff there. Okay, we dropped the second I word, which is ions. We also dropped this term called ionic bonds, and then we even added ionic compounds as a phrase. Now, let's talk about compounds for a minute because it's part of the terminology that someone knowing about life and matter should understand. A compound is when you have 2 or more elements bonded together. And again, they do that because they're looking for partners to become happier. When they find this partner or this group of friends, they become happier atoms than they were by themselves. This picture here is a representation of some common ionic compounds. Although they're strangely colored powders, we'll get into their importance to the human body and just life in general in a little while. Okay, so we dropped the word ions too. How does an atom become an ion, there it is, to then become a part of one of these bonds? And to understand it, we have to know more about electrons. Electrons are really the key here. So not only do atoms from the periodic table have a different number of total electrons, but there's different numbers of a special kind of electron called a valence electron, okay? Now, valence electrons are we call them outer shell electrons. So this red dot here symbolizes the nucleus. These black rings represent shells of electrons. They're electron energy levels. And you can see on the first level, we have 1, 2 black dots, 2 electrons. And then on the second level out, you got 1, 2, 3, 4, 5, 6, 7, okay? These electrons sit on this particular atom's valence shell, its outermost shell. Now, here's the thing. Doesn't it seem like there could be just one dot missing right here? Okay, doesn't it kind of look incomplete? And if you think it kind of doesn't look as symmetrical as it could, it's because this is an unhappy atom. First, let's figure out who this is. And to do that, all I got to do is count electrons. Ready? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 electrons, okay? And if I go to the periodic table and I see, okay, who has 9 electrons? Oh, fluorine does. Fluorine. And fluorine would love to have an electron right here, but it doesn't. So it's unhappy. So it has 7 valence electrons in its outermost shell, okay? So valence electrons are the number of electrons in atom's outermost shell. Now, another thing about valence electrons is by looking at a periodic table, we actually know some common trends and some common, we'll call it groupings of atoms, grouping of elements that have the same number of electrons based on their position in the periodic table. So if I looked at, say, this periodic table, you'll notice that a good deal of the middle is not there, but let's look at group 1, group 2. We jump over the middle part. There's another set of groups called 3A to 8A, and these are called representative elements, or some people call them 13, 14, 15, 16, 17, 18, because you start at 1, and if you count up, you get all the way to 18. But notice the commonalities as you go down the groups. These all have 1 valence electron, symbolized by a dot. These all have 2 valence electrons, symbolized by a dot. These all have 3. These all have 4, 5, 6, 7, and 8. And remember that one we were talking about right here? We said this was fluorine right here. Look at it right here, okay? Notice that this is what we call a Bohr model drawing of an atom showing its electrons sitting on various energy levels. This is called an electron dot symbol, only showing the valence electrons, the outermost shell. These two here are called inner core electrons, and they don't count in your valence shell, just the outermost shell on the outside. And here, those 7 dots are represented 1, 2, 3, 4, 5, 6, 7. Okay? And the whole group has 7, not just fluorine. Most of group 8 has 8 electrons. The one exception to it is the element that sits right here above this 8, which is helium, and it's actually sitting there with 2. But as far as the rest, you can see that trend continues down. Now, these are called transition metals in the middle, and these are special because each one of them has different charges. Sometimes they have more than one charge, and it gets a little complicated. We don't typically go too deep into that at this time, but just know those elements are there. They each have their set of dots, but they can also have different numbers of dots per element, so that makes them pretty special. All right, a little bit further on the I word, ion. So ions are atoms, it's an atom or group of atoms with a charge, okay? Now, how do you get a charge? Well, if you're a metal, you're gonna lose electrons. And when you do that, you become something called a cation, okay? A cation is a positively charged ion, okay? And that sounds kind of weird, okay? Metals tend to lose electrons, becoming cations, to be electronically stable. How can I lose something and be positive? Well, think of what you're losing. You're losing a negative charge. Let's say you have 5 protons and you have 5 electrons, and you lose one of your electrons. You now have 5 protons and 4 electrons. You have 5 positive charges and 4 negative charges. So overall, you're sitting on top with a 1 plus charge, okay? So again, we'll kind of show that over here. If you have 5p and 5e, 5 protons which are charged positive, 5 electrons which are charged negative, And let's just say one of your electrons flies away. Now you have 4 electrons, 4 negative charges, but you still have your 5 positive charges. So 5 plus minus 4 negatives means you're still sitting on top with 1 plus. You have a 1 plus charge. Okay? All right. And also, notice the word lose in its spelling. Okay? One of my other big pet peeves are when people spell lose as loose. It's impossible to lose an electron, but you can lose them. L-O-S-E. All right. Nonmetals. The stuff from the right-hand side of the periodic table. They tend to gain electrons to become what is known as an anion, and they're to become electronically stable. All right, so again, it sounds kind of weird. How can I gain something and have a negative charge? Well, let's go back to our scenario where you have 5 protons and you have 5 electrons. Someone gives you an extra electron, and now you have 6 electrons. You have 6 negative charges, and I have 5 positive charges. So what's negative 6 plus a positive 5? It's negative 1, and that's how you'd get a 1 minus charge. With charges, we usually write the number in front of the sign, okay? So ultimately here, that's how we wound up with a 1 minus, and here's how we wound up with the 1 plus, okay? Circle that up there. All right, now, what my writing is totally covering there is who is the most stable on that group. So the most stable group on the table is group 18. Everybody wants to be like group 18, that last one to the right, okay? Because all those elements are called the noble gases. They're really stable, okay? And to get there, your unhappy atom will typically gain or lose as many as it takes to have the same number as an element in that group, okay? And when it does that, the atom that forms the ion will not change its identity. It will just resemble a noble gas in terms of its electrons. All right, so let me show you what all that means. Let's go back to our friend fluorine over here, okay? We said that fluorine had 7 valence electrons in its outer shell, right? So it had 1, 2, 3, 4, 5, 6, 7. It really, really wants another electron, okay? So fluorine is sitting at 9 protons, 9p plus, and it currently has 9 electrons. So remember, all atoms are neutral. In its valence shell, it has 7 because 2 wind up being inner core, okay? But it really, really wants that 1 electron so it can be like neon, its friend who's so cool and so stable, right? It's a noble neon. And how to get that is by gaining an electron. So fluorine currently has 9 electrons, okay? So this is a plus, by the way, there. And if it could get just 1 more from somebody, 1 more electron, then it will have 10 electrons, just like its good friend neon. And it will go from being an unhappy atom to a happy ion, okay? 9 protons plus 10 electrons is what? What's 9 plus and negative 10, basically? It's 1 minus when you add them together. So fluorine winds up being happy by becoming a 1 minus ion. And I'm going to write that above it to the right, superscripted. This is happy. This fluorine atom in the table is unhappy. It's happy because it found an electron, and now it has 10, just like neon. It's still fluorine. It's an ion of fluorine. It's not neon, but it has the electron count of neon. Next, let's do one from the other side. Let's talk about calcium, okay? So here's calcium, atomic number 20. And calcium has 2 valence electrons in its outer shell. So it looks like this, okay? Now, calcium can either gain 6, and I'm going to go ahead and just for now, I'm going to kind of do this to this metal region, and we're not going to count these over here for a second because it just it can be confusing. Calcium can either gain 6 by doing this, by jumping over this stuff and going 1, 2, 3, 4, 5, 6. And it could be like krypton, a happy atom. Or calcium could lose 1, 2, and be like argon. So the question is, what's easier, gaining 6 by jumping over this set to be like krypton, or losing 2 electrons to be like argon? I'm hoping you're thinking losing 2. All right, so calcium has 20 protons, and it currently has 20 electrons, which it doesn't like. Let's say it can get rid of 2 electrons, and now it has 18 electrons and 20 protons. Okay? There's my P. If it does that, who has 18 electrons? Argon does. So we lost 2 out of the 20 to give us 18, and now calcium has the electron count of argon. Now, if we went ahead and did the math and said, okay, what's 20 positive and 18 negative? It's 2 plus. So calcium will ionize and become calcium with a 2 plus charge to be a stable and a happy calcium ion. Fluorine went from being periodic table fluorine, unhappy and sad, to gaining an electron to get 10, just like its buddy neon, to become the F1 minus anion. Okay? Remember, positive ions are called cations. This is the calcium 2 plus cation, and this is a fluoride 1 minus anion. Okay? So you can do that with basically anything up here, okay? We could do it with oxygen. Oxygen is sitting at 8. It's unhappy. It could either gain 2, 1, 2, or lose 1, 2, 3, 4, 5, 6 to be like helium. What's easier, gaining 2 or losing 6? Well, of course, gaining 2 is easier. So if it gets 2 more electrons to its 8, it'll then have 10. So we could say like oxygen currently has 8 P's and it has 8 electrons. If someone gives it 2 more electrons, it'll have 10. There we go, 10 electrons, just like neon. But it will still have its 8 protons because it's oxygen. What's 8 positive and 10 minus? Well, it's -2 or 2 minus. So oxygen becomes stable as a oxygen 2 minus anion. Okay, that's how we form ions. Okay, now you can also figure a whole bunch of stuff out based on a symbol too. Let me give you an example. Let's say we have neon. Okay, neon is a 3 minus happy ion. Let's say that it has, we'll say it has a mass number of 15, and you were asked to find the number of protons, electrons, and neutrons from this one, okay? Putting it all together. You would have to go ahead and take the mass number and subtract the atomic number for it to get the number of neutrons. So I know nitrogen is 7, that's the number of protons, but and I could even write it in here, 15, put 7 down here, 15 minus 7 is 8. So this has 8 neutrons. Now, with electrons, on the periodic table, it shows 7 because all atoms are neutral. But when it ionizes, it needs to gain 1, 2, 3 more. So it has 10 now. Okay? So we have 7 protons, 8 neutrons, and 10 electrons based on the 7 plus 3 extra ones to give it a 3 minus charge. So sometimes you'll get a symbol that looks like this, and you have to decipher what all that means by subatomic particle numbers. Let's do magnesium real quick. Magnesium has a 2 plus charge. We'll say that it has a mass number of 25, and you have to figure out P's, N's, and E's for this one. All right, protons. Well, magnesium is atomic number 12, so it's got to be 12. Neutrons. There's a 25 up there, so if I put my 12 down here and subtract, 25 minus 12 is 13. Electrons. Normally it has 12, but notice it has a 2 plus charge. 2 plus means it lost 2. 1, 2. Now it has 10. Okay? Just like neon. So electrons, 10. So we got 12, 13, and 10 as we take apart this nuclear symbol showing isotope, mass number, and ion number. Okay? Try to practice those as much as you can. Now, ionic bonds form from 2 ions where they're both unhappy and one wants what the other one has. So when two or more fitting partners find one another, one will give up electrons and one will gain electrons in order to form a neutral unit. Okay? So in this one, this would be lithium. Lithium would have 3 electrons, but notice how that third electron's in its valence shell. And it wants to get rid of it, because if it does, it's going to make this one over here happy, and itself will become happy by looking like neon instead. If it loses that third one, neon's in group 18, and neon's a happy atom. This one here, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is fluorine again. And fluorine, you can tell it could really use that extra electron in order to close out this ring, and it could look a lot like neon if it did. So if that transfer happens, these two fitting partners, it will happen. Fluorine will become a negatively charged ion, and when lithium loses that electron, it becomes positive. And what do positives and negatives do? They attract each other, and these two will stick together as a binary compound called lithium fluoride. All right, here's another one showing sodium. Sodium has 2 inner core electrons, 8 on the outside, and 1 in its valence shell. It doesn't want this 1. It doesn't want to have to gain 7 more. So it's going to give up its single electron to someone else, okay? And by giving up that electron, sodium becomes charged as an ion, a sodium cation. And then down here, let me go ahead and erase some of the pen. We have fluorine again. Fluorine could use that 10th electron because it currently has 9. So, maybe this extra electron right here from sodium will give it to that fluorine. And now we have NaF. When sodium and fluorine with its 1- charge bump into each other, they'll stick, positive and negative. This is called sodium fluoride as a binary compound. So they're very fitting partners. Some other fitting partners that are out there. Sodium chloride, very common one in living things. Barium sulfide, lithium fluoride, and aluminum nitride. Okay. Now the reason why, I'll show you. 1+ on the sodium, 1- on the chlorine. Barium forms a 2+, sulfur 2-. 2-. Lithium 1+, fluorine 1-. Aluminum 3+, nitrogen 3-. Okay? If you take each one of those individually and you try to figure out what makes them happy, what you find out is if you're a metal, you're going to lose your electrons to look like those noble gases. If you're a non-metal, you're going to gain electrons to look like that element on the end of the row called a noble gas. And then look how fitting these partners are. Okay, 1-to-1 ratio in this case. Now, is everything a 1-to-1 ratio? Answer, no. There are plenty of compounds out there that don't fit a 1-to-1 perfect match, but that's a discussion for another time. Here's what sodium and chlorine look like as they bump into each other. The single electron gets dislodged from the sodium atom, turning it into a sodium cation, and the chlorine atom gladly accepts it to become a chloride anion, and then the two of them stick together. That's called an electrostatic attraction. Maybe this is a little cuter here. Let's follow our little scene. He says, I have only 17 electrons. I feel so much better if I had one more. And she says, I have an extra one here. You can take it. Wow, are you sure? She says, yes, I'm positive. All right. She gave up her electron, becoming positive. He accepted it, becoming negative, and then they formed a cute little bond together. All right, ionic compounds for the most part are typically hard, brittle, crystalline solids. The one that we're most familiar with, of course, is sodium chloride or table salt to most of us. But importantly, biologically, when they dissolve in aqueous solutions like water, they conduct electricity. And your body needs to conduct electricity in order to work properly, whether it's your heart beating or your brain working. You need that to happen. Okay? When they do separate in water into their respective ions, they are called electrolytes. And you may be familiar with some popular beverages that have electrolytes in it. And when you're not feeling well or you're dehydrated, you drink one of these fluids that has electrolytes in it to replenish what you've lost, perhaps through sweat. There's also plenty of dissolved electrolytes and ionic compounds in the portion of blood that's liquid called plasma, this yellow colored fluid. If you take out all the red blood cells, what you're left with is plasma, and it's full of dissolved salts as part of the fluid. When you put something like a salt inside of a water, we'll call it a beaker of water here, immersed in water, the water molecules are going to go on the attack, pulling off piece by piece what we find in the sodium chloride crystal. So this here is our ionic compound, sodium chloride, aka table salt. And notice that these little red and white, what almost look like Mickey Mouse heads, those are water molecules. And they're pulling off ion by ion your chloride ions and your sodium ions into the solution itself. So it's basically breaking apart that crystal into its respective pieces. And these, by the way, these are called solvation spheres. To be completely surrounded by water molecules and pulled off, you form a solvation sphere. These salt crystals have more attraction for the water than they do for each other. All right, to summarize ionic compounds, they're made of metals and nonmetals together. Metals lose electrons, nonmetals gain. Those are also known as cations and anions, and they're found in crystals when they're not immersed in water. Sometimes many do dissolve in water and aqueous compounds, and some don't. So I just wanted to put that out there too. But when they dissolve, they're very biologically important. And ionic compounds follow what's known as the octet rule. It guides bonding in chemistry, which basically says that all those elements we were talking about are trying to gain 8 valence electrons. So whether you were on the left or the right, your whole goal to be happy was to get 8, just like those noble gases we saw on the very right. Hydrogen and helium are different though, because they only have 1 electron for hydrogen and 2 for helium, and they're actually happy that way. All right. Covalent compounds. Covalent compounds are also known as molecules in our biological world. So we'll get the terminology right on that. It's not like an ionic crystal. This is actually a flexible molecule that we're mostly made of, at least our species. So, and actually every species is. You're a lot more molecular than you are ionic. A molecule is 2 or more atoms covalently bonded together. A covalent bond is a chemical bond formed from a sharing of valence electrons to achieve an octet. So we're not actually giving electrons away and taking. Instead, we're sharing between 2. So if you look at these molecules here, notice carbon with this 1, 2, 3, 4 valence electrons. It could gain 8 if these 4 hydrogens would come in and collide at these angles, and then it can share 2, 2, 2, and 2 to form 8. And remember, hydrogen is happy with just 2. When you have 2 shared electrons, we replace it with a single dash called a covalent bond when we're writing out molecules in biology and chemistry. Here's another example of a water molecule, okay? Water molecule is 3 atoms covalently bonded. If you look at oxygen, 1, 2, 3, 4, 5, 6, man, it would really like 2 more to get 8. And if there's 2 hydrogens nearby, these 2 can come in here, collide, and then they all can share together. 2, 4, 6, 8 for the oxygen, 2 for this hydrogen, 2 for this hydrogen, replaced with single bonds, everybody's happy, okay? Here's the electron dot symbols. 2 hydrogens can stick together to be happy, like this. You can have 2 chlorines stick together because you have 7 and 7. And if they collide, we got 2, 4, 6, 8. 2, 4, 6, 8 for each chlorine. Replace the shared pair in the middle with a single dash. And you can mix and match. This chlorine has 7, this hydrogen has 1. If they collide, you got 2, 4, 6, 8 around the chlorine, and you have 2 next to the hydrogen, so everybody's happy. We call those shared pairs of electrons bonding pairs. These extras that sit on the outside, these are called lone pairs, and they're like leftovers. But they're fine. These molecules are definitely happy together. By the way, this is a hydrogen gas, a chlorine gas, and this is hydrogen chloride. Now, with sharing, you can share evenly or you can share unevenly. Now, I'm going to do that again. Look at these two atoms coming together. There's one with its electrons, another. Their electron fields come together, and this is now symmetrical. Okay, you got even blue on both sides. This is like the electron field. We call that being nonpolar. It has nothing to do with how cold it is or where it's found on the planet or anything like that. Polar is the degree of sharing of electrons. But sometimes it's not so equal, and there's a bit of an electron hog. Look at this atom. Now look at this one. This one on the right is hogging up all the electrons to make the big field around itself and leave just a little bit for this one over here. That's what's called a polar molecule. So even sharing is nonpolar, unequal sharing is polar. And let's contrast that with ionic bonds. Again, that was when you have a positive and negative ion connecting together and linking due to opposite charge. These guys here are sharing electrons, okay, sometimes evenly and sometimes not. So think of it like a couple of H's tugging equally on that rope with two electrons. Here's a chlorine winning the battle against the hydrogen here, pulling the electrons towards itself. That would represent a polar covalent bond. And here you can see we got balloons, a negative and a positive, and they're going to come together due to the opposite charges they have. And last but not least, we have a few molecules here. We just saw hydrogen and chlorine. Chlorine, if you just look at its electron dot symbol, it has 7. Hydrogen just has 1. You can see the majority of the electrons are around the chlorine, so this would be polar. With water, you have oxygen, and you have 2 hydrogens, and you have 6 valence electrons in its outer shell. Each hydrogen comes in. So when they squeeze together to form that water molecule, the majority of the electrons are on the oxygen, which means that water is a polar molecule. When 2 oxygens are together, basically what's going to happen is they're going to share a whole bunch, 4 electrons in the middle. They do something special called a double bond. And as you can see, they're symmetrical. It's not like one side has more than the other. If I put a line down the middle, a dotted line, you can see it's equal on both sides. So this would be a nonpolar molecule. And that matters because it determines what can go into cells and what can't go into cells based on their chemistry. Okay, so I'm going to end the lecture there. Hopefully you can fill in a lot of your notes based on what we just covered. And there's a lot more to come, but we're going to make this the ending point of our talk today. And I'll talk to you at the next one. Bye-bye.